Have you ever stopped to wonder how something like rust just appears on a car? Or how striking a match creates a burst of light and heat? Well, it all boils down to something amazing: chemical reactions. Today we're going to break down exactly how these incredible transformations happen, and really, how they shape just about everything in our world.
So, here's our game plan. We're going to start with the basics. What even is a reaction, and how can you tell one is happening? Then we'll get into the main recipes that reactions follow, the really important art of balancing the books, chemically speaking, and finally, how we can actually influence their speed. All right, let's jump right in.
Okay, first things first. Let's get right to the heart of it. When we say chemical reaction, what are we actually talking about? What's going on at the molecular level?
And here's the key idea. A chemical reaction isn't just about mixing stuff together. Nope. It is a complete and total transformation. You start with one set of things, and you end up with something brand new, something with completely different properties. You know, it's kind of like baking a cake. You put in flour, eggs, sugar, but what comes out is a cake. You can't just unbake it to get your flour and eggs back. So, what's holding all this stuff together in the first place? Well, it's something we call a chemical bond. You can just think of it as the superglue that holds atoms together. And during a reaction, this is where all the action happens. These bonds are going to break, and new ones are going to form.
It's really like a three-step dance. First, the old bonds break apart. Second, all the atoms get shuffled around, finding new partners. And third, new bonds snap into place. That simple process, break, rearrange, reform, is what gives you a totally new substance at the end.
Okay, so this is all happening on a scale that's way too tiny to see. So how in the world do we know a reaction is actually taking place? Well, it turns out there are some classic telltale signs you can look for. And here are the four big ones. If you see fizzing and bubbles, or a sudden weird color change, or maybe a solid that just seems to appear out of thin air from clear liquids, yeah, those are all dead giveaways that a chemical reaction is going down.
Take this, for example. If you drop a little piece of zinc metal into some dilute sulfuric acid, you'll instantly see it start to fizz and bubble like crazy. That fizzing, that effervescence, is actually hydrogen gas being created right before your eyes. It's a classic, can't-miss-it sign of a reaction.
Here's another obvious clue: a dramatic change in color. So you drop an iron nail into this bright blue copper sulfate solution, and you come back a little later, the solution is now a pale green. That's not because you mix colors like paint. No, it's because a brand new substance, iron sulfate, has been formed.
Now this one is really cool. You can take two liquids that are as clear as water, silver nitrate and sodium chloride, and the moment you mix them, a cloudy white solid just appears. It's like magic. That solid is called a precipitate, and it's an undeniable sign that a new substance has been created.
All right, so now we know how to spot a reaction. But how do they actually work? Well, it turns out that most chemical reactions follow one of four basic patterns. You can think of them like the four main recipes in a chemistry cookbook. The simplest recipe is called a combination reaction, and it's exactly what it sounds like. You take two or more simple things, let's call them A and B, and they combine to form one single, more complex thing, AB. A perfect example is burning a magnesium ribbon. It combines with oxygen from the air to make that white powder magnesium oxide.
Next up, we have the exact opposite, a decomposition reaction. This time, you start with one complex thing, AB, and it breaks down into two or more simpler parts, A and B. Just think about heating up limestone, which is calcium carbonate. It decomposes into two simpler substances, calcium oxide and carbon dioxide gas.
Now for a displacement reaction. In this one, a more reactive element basically cuts in on a less reactive one. So in our little formula here, A is more reactive than B. So it comes along, pushes B out of the way, and bonds with C, leaving poor B all on its own. And finally, we have the double displacement reaction. Honestly, the best way to think of this one is like two couples at a dance who decide to swap partners. The positive part of the first compound pairs up with the negative part of the second, and vice versa. They trade places and form two totally new compounds. Okay, now for a really crucial skill for any chemist: balancing equations. This is all about respecting one of the most fundamental laws of the universe, the idea that you can't just create or destroy matter. What you start with, you have to end with.
Let's take a look at this super famous equation for making water from hydrogen and oxygen. At first glance, it looks fine, right? But is it actually balanced? To find out, we have to do a head count of the atoms on the left side, the reactants, and compare it to the right side, the products.
All right, let's do the count. We start with 2 hydrogen atoms on the left, and we have 2 on the right. Okay, so far, so good. But wait a minute. Look at the oxygen. We start with 2 oxygen atoms, but on the right side, in our water molecule, there's only 1. Where did the other one go? It can't just vanish. This equation is unbalanced.
So how do we fix it? We use what are called coefficients. These are the big numbers we can put in front of the molecules. We can't change the H2O itself, but we can change how many of them we're making. By saying we're going to use 2 hydrogen molecules and 1 oxygen molecule, we end up producing 2 water molecules. Now let's count. 4 hydrogens on the left, 4 on the right. 2 oxygens on the left, 2 on the right. Perfect. The chemical books are balanced.
All right, for our last section, let's talk about the real influencers of the chemical world. These are the things that don't just take part in reactions. They can actually start them, speed them up, or even slow them right down.
This special substance is called a catalyst. You can think of it like a chemical coach. It gets in there, helps the reaction happen much faster or slower, but when it's all said and done, the catalyst itself is completely unchanged. It's ready to go again.
This is just a perfect analogy. The friend on the scooter is the catalyst. They helped the reaction, you getting to school, happen way faster than it would have otherwise. But your friend didn't go to class for you. They just helped you along and then went on their way, totally unchanged. That is exactly what a catalyst does.
And what's interesting is that catalysts can work both ways. A positive catalyst, like using iron to make ammonia, is all about speeding things up. But you can also have negative catalysts, sometimes called inhibitors, which do the exact opposite. They put the brakes on a reaction, like how a little phosphoric acid keeps hydrogen peroxide from breaking down too fast.
You know, from your body digesting food to your brain firing off signals, your entire life is just one giant, continuous symphony of chemical reactions. That wraps up our tour of their amazing world. The only real question left is, what part of this incredible chemical factory are you going to explore next?